Hello world. So, the last time I had been, I don't know, I spent a lot of time struggling with 52. Um, so I'm going to go back over that and I'll tackle these handful of problems. I don't remember the details on like 55, 56, but I'm pretty sure these things will fall out. 57 I did last night. Um, it wasn't bad. So go hopefully over like all of these. I think I also had done 58. I started to work on 59. It gives you this hint. Um, so yeah, the only one that I haven't seen at all, I did about half of 59. I didn't get to the log part. Um, so here, I'll show you what we're looking at today. 52. And then after you get 52, you can apply it 53, 54, 55. So 54 and 55 are like with appropriate values for z. You can kind of imagine it, just pick what z would make that series happen, and it should fall out from the result in 52. 58 or 56, I think maybe 55 potentially also. I think the two of those maybe involve an earlier result that I had forgotten about. So I had to look at when I look at the solution, it obviously reminded me of an earlier result. And then 57 is just switching gears, sort of a different problem. I don't know if clearly the right-hand side kind of looks like what we were doing, but there's a negative there. I suppose you could yeah, never mind. So, we'll see. I'm going to try to go over all these today. Hopefully have more luck today than the past couple sessions. 58 is basically the same as 57, but it says make a power series for that function. I believe you can just use that functional equation. So assume you've got a power series, use that equation. I believe that's what I did. And then 59. Oh, there you go, 59. That's a unique one, I guess. But it does kind of have the same flavor as the stuff that we've been looking at. I think it's another special case of 52. So we'll see. And then after you do 59, it mentions well, I suppose if you use your function from 57, this function, with q to the negative n plugged in, you'll produce this stuff. This 57 function. You can make this look like that. I guess once you get the coefficients, you'll probably see that. So the only one I haven't looked at all is 60. The other ones I have tinkered with, but we'll see how it goes. So yeah, from the top, 52 is maybe not as bad as it looks. And then we're going to be using number 19 as well at some point. So I had proved this by these are all odd powers down here. But on the left it has everything. So I had proved this by multiplying because each time you get a difference of two squares when you get like an addition times a subtraction, right? And it's only for the odd ones. So for all the odds, starting at 1, you're going to get a difference 1 minus something squared, or 1 minus basically things of the form 2k for an odd k, right? You get a difference of two squares where the original power was odd. So like this guy then captures all powers of 2. 1, 2, 4, goes to 8. So that's the way I had done it, is it's getting all powers of 2, all powers of 3. Well, let's see, 3 goes to 6, and then you do that and you get 12. So it's not really powers of 3. But you can see you're going to get a 9 over here as well, which is 3 squared. So I just kind of noticed that you're getting every prime factorization. Like you're representing every number. It was a pretty bad proof. I didn't prove it very well. He's got 3 different proofs, so we might go back over 19 at the end of today. So first thing first, 52, we've got this series. We did this like the past 2 days. I'm going to do it again. Although, you know, it's funny. Maybe I won't go back into it with my... Can I leave it here? Damn. Sure I left my notes here. Nope, that's not it. Huh. Well, here's a rough sketch of how to do it. Looks like I left my... Yeah, I had other notes where I did it slightly differently. I did it by splitting into 2 functions, like f times g. And I just wasn't familiar with the result at the end. So yeah, here's the original function. If you plug in q squared z into the function, here's the original function. We're trying to show that this equals a power series, or I guess perhaps a Laurent series in this case. But the coefficients c are symmetric, they're even. So we're supposed to find those coefficients c. If you plug in q squared z into this function, it'll shift, and these were just odd powers anyway. So it'll shift by 2, you'll get the next odd power. But the thing is, you'll be producing an extra one of these. This guy. And for the reciprocal side, when you plug in q squared z, on the very first factor, you get 1 plus q inverse z inverse. So that's also extra that didn't used to be there. And you'll be losing this first factor. You won't see that represented anymore when you plug this in. The first factor you get is this, right? Oh no. And you'll be also losing the last reciprocal term when you plug in q squared into this. Let's see. Oh, you're taking the reciprocal, right? So it actually subtracts 2, so you get 2n minus 3, which is there, but you don't have this guy anymore. So we would need to multiply by this and multiply by 1 plus qz. And that's what you're seeing represented there at the bottom. So this times that times phi of q squared z will get you, well, it'll almost get you the original stuff back. The difference is you'll also have a couple extra terms. So you'll have this one extra odd term, and you'll have this one lesser, that guy right there. This one sort of lesser reciprocal factor that wasn't there. So we want to divide by those and multiply by these other guys that we're missing. So that's where this functional equation comes from. If you multiply by qz over qz, this will cancel. And this will get cleaned up a bit. It'll be, I guess, qz plus q to the 2n, and that's it, right there, okay? So your relation is like this. Looks like that. And then one thing you can see immediately is if you were to expand this, the largest power of z you get is, let's see, here's like q1 up to qn minus 1, right? So that's n terms. There's n factors here with a z. There's also n more factors with a z inverse, like 1 over z. But the point is the largest value of z that you'll see, the largest degree, is n. And that's why we're stopping here. But also the coefficient for that guy would be q to the 2n minus 1, right? It starts at q times q cubed times q to the 5th times q to the 7th, all the way up to q to the 2n minus 1. The sum of those is n squared. So that's why just even at the beginning, you could observe that Cn is going to have to be q to the n squared. You know that from the outset. We don't know C naught at the outset. Notice you can't plug in z equals 0, for instance. You could plug in 1 and negative 1. And get an average, but that doesn't really help us. So you know, you have answers for what C naught is, but you don't have a nice, clean, closed form of it yet. But we do have an answer for Cn immediately. I made a little comment here. You can just see that by inspection. So, if you were to look at, say, the coefficient of zk in this functional relation, right? So assume that it's a power series, and you know, do this out. When you have qz against q squared z, well, for the kth term, right? So it's q to the 2k, z to the k, first of all, is the term that you're looking at. So for one of the coefficients, you get q to the 2n times what I just said. Q to the 2n times q to the 2k ck. That's your typical zk term. However, we also multiply by qz, and the z sort of shifts it. So you know you're going to see, you're basically dealing with the term z to the k minus 1. So it has this coefficient. It's also got q to the 2, not k, but k minus 1. So that's where that junk is coming from. This term comes from qz times your power series. This time it's phi n at q squared z. So this part is the qz times that, and this part is the q to the 2n times that. That's your left-hand side. Your right-hand side has got 1, that's just ck, and then q to the 2n plus 1 times z times the original series. So I got q to the 2n plus 1 times the previous term. It's the same idea as on the left-hand side. So that's what a typical coefficient of z to k would be on the left-hand side and on the right-hand side. You just equate those. You could just juggle those around with your algebra. You'll get this statement. And then you can see that this guy will be in the denominator in your formula. If you were to solve for, say, Cn, you could just iterate this formula that we got for the ck's, right? So we have a recursive expression for the ck's. You know, I didn't do anything here. I just factored the q to the 2k minus 1. So you get this recursive relation for the ck's. In particular, for Cn, which we know is this, But if you go all the way back down to C naught, it would look like this. And the only thing you can really do to clean this up is that the product of all these odd powers of q is going to be the sum, q to the n squared. But we also know that Cn is that, which means that this junk is 1, and that gives you a formula for C naught. And that's about it. If you plug that formula, because the reciprocal of this product. Remember, this is a finite product in this case. If you take the reciprocal of this to be your C naught, and you plug it in over here, a handful of things will cancel. I mean, for an arbitrary CK term. So I'm not going to go through the details of that, but that's how you're getting this formula. So this was the relation we just talked about. This is that observation that Cn is q to the n squared. And then I had been a little stumped on this. I had it upside down. It looked very similar. But yeah, that's because I didn't know what C0 was. Once you solve for C naught and plug it into your expression, this'll be what pops out. So like, say this was k equals 1 to n. We're saying C0 here is, let's say if you started at 1, you'd get 2n plus 2. If you go up to n, you stop at 4. So in the numerator of C naught, you have 1 minus q to the 2n plus 2, all the way up to 1 minus q to the 4n. And downstairs you have a bunch of these guys. At 1 you get 2n, and then it decreases. At k equal 2 you get 2n minus 2, all the way down to, at n you'll get q squared. So that chunk is the C0. And then you have, recall there's also a q to the v squared for your v term, for your v coefficient. So we're basically just about to write this chunk again, the product of, so say downstairs you'll get 1 minus, when you start at 1 you get 2n plus 2. And we stop at 1 minus q to the 2n plus 2, I guess k, okay? I realize that notation's kind of funny, but say we let j go from 1 to k, and this is 2j. The last term would be this guy. Upstairs we get, well, the sum of these odd terms, right? At 1 you get q, at 2 you get q to the third, all the way through k, so to the 2k minus 1. So that's where q to the k squared is coming from. It's the sum of those odd numbers, will be a square number. And then this guy's left, 1 minus q to the, say, 2n minus 2 plus 2. So the first term you see is 1 minus q to the 2n. And you keep adding, subtracting 2 until you get to n. So it goes all the way down to 1 minus q squared. And you're noticing, I didn't mean to plug in n, did I? I meant to stop at k. So downstairs I stopped at k. Upstairs I'm going to stop also at k. So sorry about this. This is supposed to be 1 minus q to the 2n minus 2k plus 2, like that. The point is, plenty of stuff cancels. Up here, what does not cancel is the stuff after this, right? We were adding 2, adding 2, adding 2. We get here, this cancels, and then there's a few more terms upstairs. So from the C naught, I'm saying a lot of stuff cancels, and that's why it looks upside down. It looks like this, but like the reciprocal, but some of the terms are missing, right? Well, anyway, this all works out to give you the answer that's in the book, obviously. So you can see this cancels. A bunch of things cancel. What does not cancel, say downstairs, on the left here, we don't go all the way down to 1 minus q squared. That is the last term. But the first term we see looks like it's going to be, these were decreasing? Yeah. So the last one that cancels is 2n minus 2k plus 2. That's going to cancel with somebody over here. And the first term you actually see that survives is 1 minus q to the 2n minus 2k. And then you keep subtracting 2 from those factors downstairs until you get down to 1 minus q squared. Upstairs, it looks like, again, we didn't quite make it to this term, so that's going to survive. But these guys canceled, right? This cancels with that. The next one cancels with the next one. We're adding 2 to these. The last one that cancels is this guy. So you don't see that term upstairs. You do see this one last. But upstairs, the first term you see is 1 minus q to the 2n plus 2k. Looks like it's going to be plus 2 is the first factor that survives upstairs. So that is the form of your kth coefficient, and that is the end of number 52. And just to double check here, we got something on the numerator that starts at 2n plus 2v, 2n plus 2v plus 2, right? And it ends on 1 minus q to the 4n, right? That's that numerator. And then downstairs we had something begins at 2n minus 2k, like that, and it ends on 1 minus q squared, like that. So it wasn't so bad. Really was not that bad of an example. I lost track of my paper here. Actually, just give me a second. Quick coffee break, and I'll go find my notes. Well, yeah, I lost track of. So the other way I had done that problem was to split it into two functions. Like I considered only the ones that don't involve a reciprocal, right? I just took z. So here's like half that function, and then if I multiply it by, if this is f, if I multiply it by f of 1 over z, that'll give us phi back, the one that we were considering. But in this case, I know that a naught is 1. But you can do the same trick. Like, I know that I know what a sub n is as well, right? It's just q, it's the same thing as before. An should be q to the n squared. Although in this case, a naught is 1. And then I can use this formula to find the coefficients ck. But the thing is, at the time, and it's a sum. It's a sum of a product where each of these is given by this mess, okay? That's actually all correct. There's nothing wrong with what I had said that day. And I was like, oh my god, how am I going to handle this sum? I don't have a good answer for you, except that it is a thing. In fact, it comes up, it's coming up on the next page. Gaussian binomial coefficients, which I guess I'm not familiar with. But they have this form. Okay, so they're not regular binomial coefficients that you're used to. These are Gaussian binomials. All right. And they look an awful lot like what we're dealing with here. It's basically like this AI is like a Gaussian coefficient in q to the q squared. So I'm not going to talk any more about that, except to say that like my approach was actually not far off. It was complex, but it's not wrong. It's just that I'm not familiar with that notation. And I don't know if he had a reason for not explaining it that way, except that maybe it would be kind of an open-ended answer. Maybe not as satisfying to do it that way. So I'm going to get rid of some of this paper. Seeing if I can use some of it. Yeah, these two are not too bad. I'll use the back of this also. About to destroy all my notes. That'll work. And it's like I did 57. Oh, no, that was me struggling with 57. All right, so I don't have it written down. That's good. That's fine. I'm going to redo it. All right, cool. Can now get rid of all these. Oh, got some more paper. So that's 52. Two different ways. Yeah, this was my scribbles yesterday. I'm trying to redo these. We can get rid of this one. What is this? Dave is very confused. All right, yeah, we can get rid of these. All right, we're moving on to at least 53. 53. Deduce the following from 52. So we've got our familiar q to the n squared. What's changed is that we're now taking an infinite product instead of just, in the previous example, this was a finite list. Notice there's no dot 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 at the end. So we stop at the nth factor. But now we're going to go off to infinity. So the left-hand two factors are what we were dealing with already, and then this looks like almost the denominator that we just had. And then he wants you to show that it equals this. Now his answer, if I recall, he basically just says like, yep, take the limit in 52. Take limit as n goes to infinity. You can certainly do that. And what'll happen when your coefficients, q is less than 1, so every single one of these in the numerator, every single one of them has a q to the 2n as a factor right there. So as you let n go off to infinity, just for this coefficient, as you let n go off to infinity, you do get some terms here, like 1 minus q squared. The denominator is still there, and that's why it does show up in your answer in the question for 53. But the point is, upstairs, each of these just becomes a 1. As n gets large, you're just getting 1 in the numerator. And then, so for the kth term, you're getting q to the k squared with this denominator. Now you are also seeing like these sort of also go away, but some of them don't, right? Some of them start off with small powers of q. So it's not like those all vanish. Upstairs, they absolutely vanish. They just go to 1, every one of those. Downstairs, not as much. If you want to picture like the tail end terms, but for the kth, well, yeah. So I'm forgetting, I had said something to justify this to myself a day or so ago. But that's the gist, you know, that you'll have these terms that begin at q squared. Yeah, I wouldn't split that up or anything. So let's see something real quick. I'm looking at 53, just trying to make it a touch more rigorous. We know this. If we had gone from, say, k going 1 to n of 1 plus q to the 2k minus 1, 1 plus q to the 2k minus 1 z inverse, right? So we know that this is I guess, well, so how does he phrase it? He does negative infinity to infinity, so I guess we'll do the same. We'll go negative n to n with a z here, right? But our coefficients looked like that stuff that we just wrote down. This junk, okay? Right here. So upstairs, well, the more important part to me is the downstairs. You get q squared, q to the 4, 1 minus q to the 2n minus 2k. That's downstairs. And then upstairs, you get, well, we know that they go to 1, so I hesitate to even write them. But you do get q to the k squared. And then there are these terms like 1 minus q to the 2n plus 2k minus 2 up through 1 minus q to the 4. 4n, like that. But as n goes to infinity, those are going to go away. Those are kind of the only ones that go away. So I just wanted to like verify that when I multiply this, I mean, is that very clear? I guess it's kind of clear. So like right now, we could multiply by all the terms up through n. Like if we plug in n here, you get, that's strange. Oh. Does it cancel? No, I'm sure that's the right formula, but yeah, you're just not supposed to use this formula for n. Yeah, it doesn't cancel. You just don't use this formula. For n, you get directly q to the n squared, right? So I'm just thinking, can I like, is it obvious that I can just multiply by this denominator right now? Because it changes as k changes. First of all, this formula works for, I guess I'm lying, right? It doesn't actually work for n. It works up to n minus 1, and then it switches to be q to the n squared for that last case. But in any case, at 0 we got C0, which was this kind of mess. I mean, you can see it from here. But at 0 you go sort of all the way up to 1 minus q to the 2n. And you actually get a little bit of cancellation, it looks like, with a term here. But otherwise, it mostly just looks like this whole thing. And on the one term, you don't get any cancellation. As soon as you plug in k equals 1, these factors don't overlap. So yeah, just be aware you can't plug in n for k in this formula. It doesn't make sense. It's not supposed to make sense. You're supposed to just get back q to the n squared. So yeah, like I was muttering, at 0, for k equals 0, you do get a bunch of terms. You get like all the terms downstairs. Actually, there's a little bit of overlap, we were saying. There's a little bit of cancellation, but you definitely get 1 minus q squared, 1 minus q to the 4. On the last term, n minus 1, it looks like the only thing you get is this guy, right? But nevertheless, we do have those terms, k equals 0, 1, 2, all the way up through n. Also, did I... No, we're okay. Yeah, we're okay. So this is always there. Like, I can clearly just multiply by 1 minus q squared. 1 minus q to the 4 kind of only shows up once you hit n equal 1. Or, sorry, k equals n minus 2, for instance, has that in it. Okay. That means the first n minus 2 terms all contain 1 minus q to the 4. And the first n minus 3 all contain 1 minus q to the 6th. Does that make sense? The first n minus 1 terms contain this guy. And the first n minus 2 contain this guy. Or perhaps I should have said n terms, since I'm sort of neglecting k equals 0 case, which contains all of them as well. So maybe I should have said n minus 1, but this is semantics, more or less. So I can definitely multiply by these, is my point. I guess what's bothering me a little bit is those last couple terms, right, that don't involve 1 minus q squared. Of course, is the reason, let's see. Yeah, say you plug in n minus 1. This just cancels. Man, how am I getting so confused here? Oh, no, it doesn't. It doesn't cancel. Good. I was a little worried there. When you plug in n minus 1, I guess it gives you 4n. Is that like the only term that it gives you? Yeah. I guess that's probably why. Did he write it backwards? No, he didn't. Oh, I wrote it wrong. Good. That makes more sense. This is a plus 2. That makes more sense. Good. So there's no overlap. Anyway, that doesn't really change any of my argument. I was going to say you can clearly just multiply by each of these, right? I can just put 1 minus q. I mean, I'd like to just put 1 plus, 1 minus q to the 2k right there. And then it would just match up, and we're done. So why don't you? Well, I mean, it definitely seems like in the limit you can, right? Because this is going to keep going off. It's like how do I know I can contain this guy? Well, because you have more than, 5 terms on the right-hand side. So as soon as you have more than n terms on the right-hand side, you're allowed to put this in there, right? Because it goes up to n. So I'm getting kind of hand-wavy here, but each of these go off to 1 as n goes to infinity. For sure. There's no argument there. So and we're multiplying by each one of these factors, like this one. As soon as you have more than one term, this is in all the terms. Like if you have... Yeah, I'm just feeling fishy about that last guy, right? Because if we actually wrote this out, the finite case, I mean, downstairs looks like this. It's the last guy that doesn't have this, right? For instance, the nth term is just this guy. It doesn't have anything in it. Did I write this backwards somehow? Yeah, you did. You wrote this backwards. So like this kind of represents the n minus 1 term. This is the n minus 2 term. And everything after that has 1 minus q to the 4 in it. But as you go off to infinity, you're seeing this term that only has the 1 factor in it. That's like going off to infinity. There is no last term. None of these, for any fixed, this is my argument over here, it was like for any fixed factor, 1 minus q to some, 2k, it's in there for infinitely many of these terms. It's only like the leading few that don't have it, and you're letting them go off to infinity. Anyway, pretty wishy-washy argument. I was just a little irritated because like when you multiply by 1 minus q4 here, you don't actually have that. Say we multiply by 1 minus q squared, because that is in all the terms. Then we multiply by 1 minus q to the 4, and it's fine for all these other terms, but the first one, or I should say the last one, the n minus first one, didn't have that as a denominator. Anyway, thinking too much about this. Especially when his answer was just like, yep, let it go to infinity. Take the limit as n goes to infinity. Period. Nothing else to say. So yeah, upstairs I've got no problem with that. And downstairs, it's true that you... Well, but this is one particular term. This is my whole hang-up, is that this is just one coefficient. We're going to have a bunch of these. So what? That means every one of them has 1 minus q to this giant power. Yeah, why are you hung up on anything? I guess that's why he doesn't have to say anything else. Yes, I'm still trying to make that a little more rigorous, but I think I'm going to move on. That kind of says it. It's the same kind of logic I was saying over here, like, if you let n go to infinity, any fixed factor of this form is absolutely in infinitely many of the terms on the right-hand side. It's actually all of the terms except for the last one, but you're letting that last one go off to infinity. Like, you're letting the index go off to infinity. So, like, what? Find me the term that doesn't have this in it, and you're not going to be able to. Like, you won't. This term doesn't exist in the infinite product. You know what I'm saying? It's like the head term that we're letting move on. Anyway, that was still a very wishy-washy explanation, but But yeah, the kind of saying that as n goes to infinity, you get roughly, like, you basically get this in the denominator, and we're multiplying by that, and that's how you end up with 53. That's the end of 53. All I'm saying is, like, where'd that factor come from? But, like, obviously it came from the denominator, and you get one of those factors for every power of n. As you let n go off to infinity, this factor is guaranteed to be in the denominator on the right-hand side. So just multiply by it, and that's it. That's the end of 53. So it's really just using the coefficients from 52 that you found, taking the limit. The numerator, they all go to 1. And the denominator, they look like this infinite product. 1 minus q to the 2n. Okay? So, yeah. I had a finite product, but now you're letting n go to infinity. And you see right there, we've got positive n. So yeah, you do get this infinite product. Like, you're looking at this infinite product on the right-hand side in the denominator. So stop thinking about it. It is what it is. All right, we'll move on. 54. This time we have, So this is going to be just playing with that, with number 53. 54 is just an application of 53, I'm pretty sure. Somehow we're going to get, oh yeah, I remember this one. Stucky helped me with this one. You just choose z so that this pops out on your right-hand side, okay? So for one thing, you see the negative sign. Z is going to be negative q to the something. And I think they also replace, because this 3n squared over 2 is playing the role of n squared. Okay, so we're going to replace q with another q. We're also going to replace z with a particular value involving q. So I'll rewrite 54. What we're trying to do with 54 is show that the product of 1 minus q to the n is the infinite sum. And I didn't write 53 down here, but anyway, 54 is the infinite sum of negative 1 to the n. Here, n goes from 1 to infinity, right? And it doesn't really look a lot like 53, frankly, right? It doesn't. Not to me. obviously it's an infinite product, and it's got 1 minus q, so those are good signs. But I would not have recognized it as relating to 53, the left-hand side. And that was the little trick that Stucky showed me, because I was like, even when I wrote it down, you'll see what I mean in a sec. Even when I did get it correct, I was like, I don't know how to show this. But the right-hand side we can do. We can make this match up pretty quickly. The right-hand side's not going to be too bad. So how do we get this q to the n over 2 immediately? You're going to let z be q to the half. Okay? Q to the negative, sorry, z is negative q to the half. And that way, you'll get your alternating, you'll get your q to the half raised to the n. So immediately you get a good chunk of this by letting z be negative q to the half. And then that means you have to do it on the left-hand side too, of course. But then they're doing one more thing. It's cute notation. He says, apparently this bar is supposed to tell me that I'm going to replace q with q to the 3 halves. You think that's a pipe? You think this is an homage from the past to Linux? He's saying, no, certainly not. But anyway, I don't know why I guess he didn't want to write q equals q to the 3n. He could have just said replace q with q to the 3 halves. But anyway, that's what he meant by this. Okay? Replace q with q to the 3 halves. If q is less than 1, then q to the 3 halves is still less than 1. Let me finish writing this junk. We had alternating, and we had 3n squared plus n, all of that over 2. So this is what we're trying to show. But you just use the result from 53 that we just kind of talked about. The result from 53 was that the product 1 plus q to the 2k minus 1, 1 plus q to the 2k minus 1 against z inverse, and then we've got this 1 minus q to the 2k. And this is equal to just the sum of, I want to say q to the n squared. Yeah, there it is, q to the k squared. So we'll write q to the k squared, z to the k. And this is an infinite sum that we had. This is also an infinite product. Okay, so that was 53. But we're trying to show something else. And all he does is replace q with q to the 3 halves. And you can see right away, like, okay, if this was q to the 3 halves, you'd get 3k squared over 2. So that's that part. That's that chunk. That was the only other piece that's missing. So replace q with q to the 3 halves, and replace z with negative q to the half, and you immediately get your right-hand side. The right-hand side is just already taken care of. So now all I have to do is show is that this left-hand side is this. Or just observe it, really, because there's nothing else to show. Like what we've seen from 53 is that this stuff will equal this stuff with these numbers plugged in. But then you have these 3 factors, and you're like, what? How does that relate to this? But it does kind of obviously. That's what Stucky showed me. So here goes. Let's plug these in. We're right side is check. With these parameters, the right-hand side matches up with this, which means it must equal this stuff. So what does it equal? The left-hand side is product of, and you get 1 plus, it's not q anymore, it's q to the 3 halves, but okay. So you'd get 3k minus, let me just do it slowly, minus half, right? 3 halves of 2k minus 1. I'm getting 3k minus 3 halves. That's what I meant to say. Good. And the z we're also replacing with negative q to the half. So this becomes a minus because of that negative, right? So that's the first factor. And then in the middle here we have 1 plus, again it's not q, it's q to the 3 halves, 2k minus 1. And then it's z inverse, so it's like, well, 1 over this, right? So let's just write it as negative q to the negative half. That's our z inverse. And then we got 1 minus q. Of course, it's not q, it's q to the 3 halves. But anyway, 1 minus q to the 3 halves times 2k. So that's a 3k. Let's see, this first one is minus, right? 3k, and we said it was minus 3 halves. So if you take minus 3 halves and you add a half, I guess we're at minus 2 halves. So we got 3k minus 1. Is that plausible? And then for the second one, it's 3k. Oops, damn it. Fucked it up. Sorry. 1 minus q to the 3k. Again, minus 3 halves, but this time we're subtracting another half, so it's minus 4 halves, so it's minus 2, right? And the last one is just 3k. And that's our left-hand side. But it was supposed to be this, right? This is evidently the product of 1 minus q to the n in general. Or q to the k, as it were. So yeah, I was staring at this and I didn't get it. I was like foiling things out, trying to make sense of it. Although I did immediately notice that it's like, they're all just mod 3, right? It's remainder 0, remainder 1, remainder 2. So maybe you're smarter than me and you immediately are like, oh, we're done. There's nothing to show. Yeah. So Stuckey was like, why don't you write out a few terms? Should I ignore the first term? No, you don't have to ignore the first one. But is this supposed to start at 0 or just start at 1? No, it starts at 1. This guy has a 1. Oh, I see. There it is. There it is. If you plug in 1 for k here, you get 1 minus q, right? So you get 1 minus q, 1 minus q squared, 1 minus q cubed. And then for 2, you get 1 minus q to the 4, 1 minus q to the 5, 1 minus q to the 6. Then for k equal 3, you get 1 minus q to the 7, q to the 8, q to the 9. So yeah, if you just write out a few terms, you know, at 1 here you get q squared, q, and q cubed. Some real high-tech math, huh? Anyway, I was like, I see this like algebra, but I don't see. Anyway, you get the idea. So yes, it does indeed equal 1 minus q to the n. I don't know how I'm ever going to remember any of these identities. Are you going to remember that this is true when you need it? Because I don't. Well, speaking of, I think the next one involves a previous result. I'm just saying that because I remember I looked at it. Yep. So I'll show you 55 in a sec. I'll see if I can do it off the top of my head without reading this, but notice it says apply 19. So like I got to that point and then I was like, I wonder what to do with this. And then I had to go look in his answer and he was like, yeah, 19. Remember what we did like 2 weeks ago? No, I don't. No, I do not. But if I were a smarter person, if I had a better memory. All right, what are we doing? 55? 55 says difference of even powers of q upstairs, difference of odd powers of q downstairs. Take that infinite product, you'll get this. And I noticed he dropped the negative powers this time. I don't want to I don't want to do any cancellations. I think this follows from stuff we've already seen. And we just looked, you might have seen it in the answer, we just looked at the answer, but I was trying to do this without, just seeing if I can remember how to do it. I can kind of see q to the half, right? Like, let z be q to the half, and you get part of that. It's n squared over 2 plus n over 2. So maybe I let q, like, what if we take the result from 53 again, and we replace q with q to the half, and z with q to the half, and then your right-hand side looks like q to the k squared. I don't know why I just replaced it with k's. But the only thing that bothers me a bit is that this was a sort of double sum, right? I mean, not a double sum, but an infinite sum in both directions. But yeah, replace it with these, and you'll get q to the k over 2 over 2, or k squared over 2, excuse me, times q to the k over 2, which is all we wanted, right? K squared over 2 plus k over 2, yeah. So other than the fact that the sum is kind of wrong, the indices are wrong, I wonder, would I get this formula with my I threw out my notes, of course. Remember my function that I had used earlier? I kept doing it my way and getting weird stuff. There it is, my f function. Grr. I'm thinking, like, go back and reconsider this function, but drop all the reciprocals, is what I'm saying. Then you won't have any negative powers of z. I don't know if that's really what he wanted. Anyway, if we take the full sum, you get this full sum with q and z being replaced with q to the half. Let's first see what you get when you do that, and I'll just forget about the fact that we have a doubly indexed. So we have this. And what, 50? Oops, we're not 53. We're doing 55. What we would have from 53 would be 1 plus q to the 2n minus 1. So it's like, if I replace q with, I just set it up here. Replace q with q to the half. So instead of 2n plus 1, we'll get n minus half. And we're also placing z with q to the half. And that's that. And then the next term is q to the 2n minus 1 again, but this time it's like this. Again, we have z being replaced with q to the half, but this is z inverse, so we get like this. And then we have that last term, 1 minus q to the 2n. But for us, it's just this. So these add, these subtract. It looks like we're getting plus q to the n and minus q to the n. Interesting. not quite what we wanted, probably. I don't even remember what how the question was. This weird thing. We're trying to get to even powers on top. Is it minus or plus? It's minus. We're trying to get to like this formula. And it's supposed to equal this. Well, with a 0 on the bottom. It's not this double sum, but yeah, this product is equal to basically this, but starting at 0. A little strange. Anyway, we know now that this equals this right-hand side. But that doesn't... Alright, I want to see real quick if he just did a direct 53, or if he... Special case 53, replace Q and Z the way we did, and then apply 19. Alright, I guess it's time to look at 19. But... yeah. See that? So there's your numerator. Oh. Yeah, but why is this a double... Like, why is this not 0? I mean, I don't think it was a typo, because in his question, he says 0. And he never makes typos. Actually, there is an errata for this book, but it's in the second volume of this book, and this was published after that. So there's no, at least to their knowledge, there's no errors in this. He corrected, I actually looked to see, there was only like 5 mistakes in the first place, but, and they were like, most of those were just silly typos, had nothing to do with any real math, you know. So anyway, that's how I'm pretty confident that this is not a mistake. He meant to start at 0, not at negative infinity. But yeah, this is a neat relation. Anyway, let me remind us of what 19 is, and if I can stomach it today, I'll try to reprove this. Because if I recall, 19 had like 3 different proofs, and I didn't really follow any of them. I did it my own way, which was very wishy-washy. But yeah, the product of, you got 1 plus, looks like a zeta. Yeah, 1 plus zeta is the product of 1 plus zeta to the k. This k goes from 1 to infinity. So it's hitting every number. The power is every natural number. If you take that product, you'll get this. And downstairs you get differences with odd powers. I don't know if you can see that. So I had done it, I mumbled something about this at the beginning of today's stream. I just multiplied by each one of those, and since these are odd, they're interacting with only the odd powers, so all your odd powers are gone, and they become a difference of 2 squares, right? They become 1 minus zeta to, 2k, where k is an odd number. But then you can keep interacting, like 2 is 2 times an odd number. And 4 is not, but when you combine these two, 1 minus zeta squared times 1 plus zeta squared, you get, it's 2 times that even number. And so, then you have 1 minus zeta to the 4. 1 minus zeta to the... 1 minus zeta to the 4 times 1 plus zeta to the 4, which becomes 1 minus zeta to the 8. And that interacts with 1 minus zeta to the 8, or 1 plus zeta to the 8. So, all the powers of 2, they do get caught up. They eventually do get multiplied by something. I don't know what a good name for that would be, but they get partnered up with a 1 minus. I hesitate to call it the conjugate, but it's that kind of a concept. So if you're odd, you're already paired up. If you're a power of 2, you're paired up. So then you just have to deal with things like... Well, you can see my point is that you actually get all... Anything that has a prime factorization is going to eventually get caught in this web of 1 minus zeta to the whatever. But that's kind of a wishy-washy... It's not a very rigorous proof. And he didn't do it that way. He proves it 3 different ways, but none of them are that. Anyway, this product right here? No, this product. I'm confuzzled. Must be this guy. That's weird. So this goes from 1 to infinity, but sadly you get, I feel like you get negative infinity to infinity on the right hand side. I guess we're just going to gloss over that. It doesn't seem to be coming up. If you multiply these two, you get the numerator. So obviously that's what we're doing. Unless I made some sort of mistake here. So at the beginning you get 2, but then after that you get exactly what he's talking about in 19. So we do have an extra factor that looks like this, right? We have that extra factor in the middle that is exactly this. And that infinite product on its own happens to also be equal to the stuff that we were missing downstairs. So we're basically done. By 19, this stuff is going to become, I mean, I'm getting a 2 in the way, right? Because at 1, yeah, this is correct. Like, when you combine these, you get, all right, let me factor the 2 out. Because if you plug in n equal 1, you get q to the 0, so you get 2 times, and then you get the rest of the stuff. So we get 2 times, and then if you want, we can just do this, right? And now there's no more 2 term. But the point is that this is the same as 1 over 1 minus q cubed, and that was that missing stuff in the bottom, that's all. And then the other 2 terms combine to be 1 minus q to the 2n, and that's the numerator, and so we're done. Well, this junk is what we have on the left hand side, and it equals this. So I'm still a little, I guess we didn't have a 2 either, right? Is this even? It doesn't. Huh. Is that all it is? Is that all it is? Just divide by 2 and it gets rid of half of the... I mean, that would be clean. That's clearly what he intended. Like, we've got an extra 2, and hey, look at that. We have twice as many terms as we should have on the right-hand side. But that's not... am I just being an idiot? Yeah, there's 2 negatives here. Why are you thinking about this? Okay. Yeah. I guess it is the same, huh? Why am I having such a hard time with this? Like if n were -3, say. Well, I guess I'm having such a hard time because it's like k squared plus k. So for a negative value, you don't get the same thing. They're not just equal. But maybe I am thinking about this too much. They do kind of give the same series, don't they? Except for 0. Except for n equals 0, which we're including. So if you start at 1, that's what I should be checking. If you start at -1, you will get the same thing that you get by plugging in 0. That's interesting. Okay. I guess what I'm saying now is if you look at this series, it's equal to this series for our particular, you know. So for instance, at n equals -3, you get this, right? But it agrees with what you'd get at 2, right? 2 and 3. It's exactly the same value. So yeah, he didn't mess anything up. He meant to write a 0 there. It's because we've got a 2 in the way. You just put a half there. It'll remove this half of the terms. Interesting. So it did work out. I guess you see why I was flipping out, of course. I was like, this is not an even function. Um, like, what about that? um, right? If you look at, what is it, this? I was basically freaking out because this is not an even function, although it is even about -1, right? It does have symmetry, it's just that it's not centered around 0. But that's okay, we're not centering around 0, we're taking these guys and those guys. Very strange. I'm still very confused. Oh, no, that's right, that's right. Yeah, a little weird, man, a little weird. So at 0 we get 0 times 1, and at -1 you get 0 times -1. Interesting, interesting. That's cute. Anyway, so 55 worked out. Of course, it also relied on this tricksy thing from page 3. You couldn't have done it without that. All right. What was that, 56? Awesome. No, 55. Yeah, it's 55. We're on to 56, which I don't know if I've done this one. I think it's going to be the same kind of thing. How are I going to get 1 plus downstairs? Upstairs looks the same. No, it doesn't. Damn, alright, it's a little different. And then we got this alternating business. And we've got squares. Alright, can I just take this? Can we use the previous result almost with an alternating? It's clearly this again, right? It's very much the same flavor. I don't know if you can see it. Sorry, 56 is what I'm looking at. Very much the same flavor as the problem we just did. I'm sure it involves 19 again. But I wonder if we should just go back to 53. Because you're seeing squares on the right-hand side. I would rather use 55. Huh. Yeah, I don't know if I can, because the denominator looks a little funky. Alright, let's see what we got. I think I'm going to go back to 53. We're looking at 58 right now. Or, damn, 56. 56. And it says we want to show that if you take 1 minus q times 1 minus q squared, is this every power? Yeah, 1 minus q cubed, etc. And you divide by 1 plus q squared. Really? Yeah, that's what it says. Okay. 1 plus q squared, etc. But this is somehow equal to 1 minus 2q plus, 2. Interesting. They're all 2. 2q to the 4 minus 2q to the 9 plus 2q16, etc. Alright. If they're all 2, that's not quite what I expected. What if I had no q at all? I'd get minus q plus, because like if I didn't have the 2 in the way, it's just this series where z is -1, right? So I wonder if he did some trickery, like, how am I gonna, or like this series, plus 1 minus itself or something like that, like this series -1 plus itself, something like that. This series plus itself -1 is what I'm saying. Well, anyway, the right-hand side is clearly q to the k squared -1 to the k, right? Except for the 2's. Except for the 2's. We could even just double this and subtract 1 if you wanted to do that. So if we throw this in number 53, double this and subtract 1, because the series in 53 I think is also like that, so it doesn't quite match up, but it's close enough, right? Oh, doesn't this double it? Of course it does. So at 0 you get 1. But then say when k is when say k is -1, you get a negative and you get q, which is that guy. So yeah, this is this series. This already is. I don't have to do anything to it. All right, and what 53 gave us was this is the same as the product from 1 to infinity, and then you get, like, I want to say 1 plus q to the 2n minus 1 z. You get a reciprocal term, and then you get that last funky term, right? 1, I think it's minus q to the 2n, this guy. So I'm quoting this, but our z is -1, and that's all. Okay, so 53 had said this, well, remember, z is -1. There's your z to the k. 1 plus q. I should have written minus immediately. Fuck it. 1 to infinity. 1 minus q to the 2n minus 1. 1. Oh, it's a reciprocal. But that's okay. That doesn't really help me. Weird. And then the last one was 1 minus q to the 2n. I believe that's right. The last one actually is minus. The other ones are plus, but we took z to be -1. So that's why I've got minus signs there. But other than that, I guess I've got the square of the odds. That's weird. I see. I don't get both of those. All right, what else can we do? Here's the evens. Okay, so we pair these up, for instance, and that's the numerator. And then this one, okay. I still don't see. I thought we had a plus when we used 19. Didn't we have a plus there? Yeah, you're supposed to. That's okay. We can fix that. Number 19 is the one that says if you sum 1 plus q to the n, it's the same as this infinite product. Yeah. Let me just triple check, but I'm starting to remember it. Unless I got it wrong. Nope, that's right. 19 says if you have a product of 1 plus a power of zeta, it's the same as 1 over the difference of all the odd powers of zeta. So it says this. So this is our numerator. I don't have to touch that. But this is somehow... Damn it. It's not quite working, is it? But I do feel... I thought we felt okay about the right-hand side. I'm pretty sure the right-hand side is just exactly this. Right? You get 2's because this is already even, actually. Except at 0, where you get 1. Right? So for instance, at k equal 2 or negative 2, you get q to the 4. And it's positive both times. So this right-hand side is the right-hand side. These two are clearly the numerator. Right? When I plug in 1, I get 1, 2, then I get 3, 4. So this is the numerator. There's no argument there. So the only thing missing is for me to demonstrate that from 19, this product... Huh. I do see this as odd. What if I no, it matters. Huh. How am I gonna... Plus, I don't want these on the bottom anyway. I want the evens as well. Does the negative matter? Oh, wait a minute. Wait a minute. I think it's the same statement. It's the same statement. The right-hand side is, so like, yeah, do you see what I'm saying? The right-hand side is obviously 1 plus q to some power. It's the same statement, just they took the reciprocal of it. Yeah, we're okay. We're okay. You see it? This is 19 again. I think we're done with that one. So this left-hand side, this is the denominator, but by 19. This is the denominator, but it's actually like the reciprocal of the statement that you saw in 19. Awesome. All right, what do you have to say about 56? Oh, not much, not much. What he says is, let z be negative 1, and use 19. Yep, that is indeed what he says. Man, that 53 is really useful. That's a neat question. All right, we're on to 57. Yeah, 57 is a little weird. It's not hard. It's much easier than it looks. So I tried to do this the other day, and I got kind of stumped in the middle, even though I don't know, I was doing it kind of straight. I know, I just did what it said, but I still got stuck. But when you see the answer, you'll see why I got stuck. It's just kind of some algebra trickery. Basically just group the terms the correct way and it'll pop out. I guess it also helps to use a particular notation. Anyway, switching gears here, 57 doesn't really seem like it relates to the previous ones. We give ourselves a new function. G is, again for sort of fractional q, less than 1. G is this function, q over 1 minus q times 1 minus z, yep. And then that squared times 1 minus z, and you get an extra factor, 1 minus qz. And then the third term, we got our friend cubed, and you have 3 factors. So it looks like your product is like 1 minus q to the kz, as k goes from sort of 0 up to whatever the current length is. So we're looking at 57. What is it, G? G. G of z is, let's see if I can just write it quick. I think of it kind of like this. I don't know if this is going to help us. K goes from 0 to infinity. And then what goes here is 1 minus q to the k times z. So on the first term, you get this, one of them, and you get 1 minus z. On the second term, the k equals 1 term, you get q squared, 1 minus q. Oh no, this is wrong. Damn it. This is actually a product of these, huh? It gets bigger and bigger. This is the last term in the product. Damn. All right. Okay. We'll do it. We'll have to write it like this. I knew there was going to be something wrong with it. So on k equals 0, you actually only get this one term. K equals 1, you get these two terms, you know? Yeah, this is more accurate. I don't love that notation, but it is what it is. Anyway, we're supposed to be showing that there's some weird functional equation. It's like 1 plus... All you have to do is show... Yeah, I thought this was going to be easy because it's like, show that this equation is true. I love those. Shouldn't it just be kind of plug and chug? So yeah, show this relation happens. 1 plus g minus g of qz is equal to this product. One plus g minus g of qz is equal to this. Is it a minus or a plus? Yeah, minus. Minus q squared. Hey, Stucky. Right, q squared, etc. Yeah, kind of early. Well, you know, early. Early. All right. Yeah, I'm reviewing these, all of the 50s. I started with 52 today. I didn't rewrite it, I just showed people my notes, but we're doing the 50s. Because a couple of these, I don't know. A few of them I had like spent a few minutes outside of stream the past couple days, so I wasn't as scared of them anymore. But yeah, we're tackling the 50s today. Trying to basically get this whole page done. And then, I don't know if I'm going to get to 60 today. That would be awesome. But I actually want to see something early, because we just used this 19 result a couple times. 19 came in handy. And I was like, I had a wishy-washy proof of it, because I noticed that like when you multiply by these denominator terms, these factors, it like those are all odd on the right. So of course they interact with all the odds on the left and they give you a difference of 2 squares. And so anytime you've got a number on the left that can be represented as like 2 times an odd. Anyway, every factor over here that's like 1 plus 2 times an odd, like that first guy, it ends up getting hit with 1 minus zeta, and it becomes 1 minus zeta to the 4. And then these two combine and give you 1 minus zeta to the 8. So that immediately takes care of all the powers of 2. And of course all the odds also get combined. I don't know, I'm not explaining it very well. But I basically reasoned to myself that every factor on the left eventually gets hit with something. It eventually is transformed into the form 1 minus zeta to 2k. So in the limit you get 1, right? Yeah, exactly. You get this. Yeah, and I was like, well, I guess that's good. But then his answers, he's got 3 different ways that he shows this. Here it is. First is due to Euler. So I think I remember I was about to say in class. In the stream, I ended up just going back over this one, I think. But yeah, his three ways of showing it are not wishy-washy like mine. He's got, oh, sorry, it was just, I guess this is the third solution. Oh, there's two here? Okay, good. So here's an answer, and here's another quick answer. All right, so if I have time today, I'll go back over those also, because for some reason, that problem didn't stick in my brain. So when I needed it for doing these 50 problems, I was like, I don't know what's going on. But then I looked in his answer, and he was like, oh yeah, just use 19. Just use 19, buddy. So it came up a couple times. Yeah, yeah. Yeah, and okay, that makes sense. I mean, I could just skip it because we did talk about it. I talked about it like a few weeks ago. Maybe I'll just go over it on my own time, or I don't know. It might be smart to try and understand the other explanations. According to 14, 14 is one of these combinatoric weighing problems. Oh, was this the one where you're like proving that you have unique, like basically that binary numbers are unique? Probably. Let's see. 14. Yep. On one pan. So, yeah. 14 was to prove that any number can be expressed in only one way using binary numbers, or, powers of 2. Yeah, any positive integer admits a unique representation in binary. Alright. Anyway, man, that Euler. Such a smart guy. Yeah, I could just use 19. You're right. So we're moving on. 57 is switching gears. It's not really the same kind of stuff. Let me see if I can screw this up. He doesn't even do this. He just starts writing them out, I think. And his answer... So here's our function g. We're going to take 1 plus this. Well, let's just start. 1 minus q z. Yep. I'll do 1 or 2 more just for the sake of it. I had tried to do this on stream last time, but I got stuck. Maybe do another term, but that's right. So that's 1 plus g, and then I also want to subtract off g of qz, which does not have a 1 in it. It does have this. So here's our g of qz. Just looks like that. And we're subtracting these. Etc. Yeah. Scribble, scribble, scribble. QZ, Q squared, and Q cubed, and we'll stop there for now. So one thing, like obviously I can do this minus that, and you'll get QZ minus Z. And here you'll group these, like on the second term, these are in common, the common factor between those two, so you'll get q squared z minus z. So we're getting like we are getting somewhere, I guess. Q squared, 1 minus q squared. And then so this one has a common factor of another 1 minus qz. But other than that, q squared z minus z. And let's do one more. This time they have 2 factors in common. And then your times q cubed z minus z. You can factor the z out, and you're looking at, the power of q minus 1. And then he did something kind of cute. like in his answer, he does something like a, I don't know, he basically just lets like AK be negative q to the k or something like that, just to clean up the notation a little bit. Let me see if I can figure out what would be a nice something like that. It might just be, no, it's not just q to the k, I don't think. I don't quite remember. We may be subtracting here. Like this is 1 minus z times the power, and then you get q minus 1, q squared minus 1. So if we instead had, if we do this, then whenever we see something like 1 minus q to the k, in our new notation that would be 1 plus ak. Okay? And you're seeing those factors down here. Oh, and our right-hand side would be what? I guess it would be 1 plus, like 1 plus akz, right? 1 minus qz would become, well, not q, but q to the k, z would become 1 plus akz if we use this notation. All right, so I'm pretty sure he introduces that notation, and then he just does some magic hand-wavy algebra, and it pops out. Basically just some grouping that's about to happen. So like this is 1 plus, well, all right, let's do another step. I've got a z. I still don't really quite see what's going to happen with these guys, but I do see that we've got this form. Do I want to subtract so it actually looks like this? I don't know if that doesn't. Yeah, let's subtract. I don't know why that would matter. Yeah, why would you care if you subtract? Why don't we just leave it? So here I have q squared minus 1, which is something fishy's going on. It's the negative of these. That's why I want it to look like this. All right, fine, we'll subtract. 1 minus a whole bunch of stuff. Yeah, I don't know. Let's see. 1 minus, what am I going to do with these guys? Q over 1 minus q. I don't see those going away. Oh, I guess they're just a, aren't they? Well, we'll take care of that in a sec. This is now 1 minus q. That's weird. Sure, keep going. Wait, 1 minus? What are you doing? Yeah, okay, that's fine, that's fine. Let's do this. I don't know if this helps me. I don't think it does. Probably a bad idea. Alright, whatever. Q squared, single z, 1 minus q squared. And then you do get this extra guy, which we're about to call 1 plus a1. But this is now 1 minus q squared. Alright, fair enough. Factored a z out, and now I took a negative of it, and that's why we have this. And then we have more. Alright, I guess by this notation, q to the k is also negative ak, if that helps. I don't know if it's helping me, but 1 minus a1, 1 plus a1? Oh, okay. And then this is 1 plus, right, 1 plus a2. Some of them cancel. Is that good for me? I don't know. What if I did 1 minus qz? That's 1 plus a1z. Man, these z's are screwing me up. AKZ, or yeah, A2Z 1 plus A1. I guess the Z is in common everywhere, isn't it? Alright. Except for the first one. Yeah, I'm trying to do this without his answer. But his answer was basically just do this. You got a bunch of factors of this. And those are the right hand. Wait, where is it? Yeah, those are this right hand side. We're trying to show that it equals, in our notation here, it equals, you know, the product of 1 plus, I guess it's this. That doesn't sound right. There must be a z here, and then I'm just forgetting about it. Yeah, I'll bet there's a z here. Because that way this... I don't know, Dave's confused. Because that way the right-hand side is just 1 plus a1, 1 plus a2, etc. Becomes a little nicer looking. I don't know. Oh, yeah, you can't see what I'm staring at. Yeah, this is that term. Well, maybe just see what you're getting. Worry about the notation in a sec. QZ minus... yeah, you see that? You see that grouping that's already happening? Minus q squared z 1 minus qz minus q cubed z 1 minus qz 1 minus q squared z. So like, if this was a1, or something like that, if this was 1 plus a1, you've got and this is a2, 1 plus a1 minus a3, 1 plus a1, 1 plus a2. Anyway, it obviously continues. You can see that we're going to get these guys. This guy cancels with the last one, so you get 3 factors this time. So down here you'd have minus a4, 1 plus a1, a2, and a3, etc. So yeah, I was supposed to let, you can see obviously I was supposed to let, oh, are these pluses? Yeah, these are supposed to be pluses, because if I'm making this plus, then I'm doing the substitution, yeah, I was close. I'm doing the substitution ak is negative q to the k z. So this is actually a plus. And this is a plus. And these are all pluses. Because the a involves the negative, it includes the negative sign. And so this is 1 plus a2 times, yeah, there it is. There it is. See that? This is 1 plus a2 times 1 plus a1. That's the first two terms. And then 1 plus a2 times 1 plus a1 shows up right there. So these three terms are 1 plus a3 times 1 plus a2 times 1 plus a1. We're basically done. This equals 1 plus a2 times the factor 1 plus a1. And then these other guys, right? But these two factors are right there. So it's one of them plus a3 of them. And a4 is times those three factors, right? Those three factors. So it equals 1 plus a4 times, you get the idea. And that was what we were trying to show, is that the right-hand side, like when you express this this function, when you jot down this in particular, 1 plus gz minus gqz, you'll get this product. So that's 57. And here I'll show it to you in nicer notation. Here it is in print. There it is, setting negative q to the nz to an. So I would not have gotten this if I hadn't seen this answer ahead of time. The other day I jotted this down and was kind of like stumbling at it, and I couldn't get anywhere. But then I saw his answer and was like, oh, that's silly. So it's really just about grouping. There's some cancellation that happens, and then you get this nice grouping. I feel like this is another one where he, like, usually he doesn't write it out like this. Usually he shows you some mind-bending I don't know, some craziness that Euler did. I'm sure he was like 12. All right. So that was 57. 56. 57, yeah, that's 57. We're on 58. Find the coefficients of the power series for G. So same function, but assume it's a power series and find the coefficients. I definitely did this one by myself. I had no problems with this one. So if you assume it's a power series and you know this relation, have at it. So we're on 58 now. We don't need the original function. We just need this relation. 1 plus gz minus gqz is 1 minus qz, 1 minus q squared z, etc. So let g be, it shouldn't involve, yeah, it doesn't involve any negative powers. It starts at d0. So write it as a power series with coefficients d, and find d. Yeah, right. So anyway, yeah, this one's not bad. I presume. I thought it was pretty straightforward. Um, just, just do it, man. So QZ in here, it's going to be Q to the K, right? So our left-hand side, actually, can we say anything more? If you plug in 0, you'll get 1 equals 1. Damn. If you plug in 0 for all the z's, you don't get anything nice. You get the sum of these. You see that? You can plug in 0, but you'll get the sum q junk plus q junk squared plus q junk cubed, etc. So for one thing, I'm noticing d naught is the sum of these guys from 1 to, I guess, infinity. Okay? But anyway, yeah, just jot this down. We've got 1 plus the series. I mean, I guess I could do it slowly. Nah, we don't need to do it that slowly. So here's one term, and then here's what you get. I guess this goes 0 to infinity. Here's what you get when you do QZ. You get the same coefficient, but you get a Q to the K. But there's no z's. Yeah, there's no like z multiplied by this, so it doesn't do any like shifting of the indices or anything like that. So we just get that times zk. And it's supposed to equal this product. Why did I think this was easy? I did this the other day and it was like, it took me a couple seconds. So it must not be that hard. Um, hmm. Okay. Yeah, you are getting like the coefficient of z on the right hand side, you get a bunch of different ways, right? Hmm. Hmm. What's the coefficient of zk on the right-hand side? It must be something obvious that I'm not seeing right now. Oh, you know what? It doesn't have to be. Like on the left, I'm seeing obviously we just get this for the coefficient of zk. But on the right, you get like every possible pairing, right? Like all the ways that you could have kz's, but every combination of them. That's pretty nasty. Huh. Yeah, I can't quite remember how I would have handled that. We've been dealing with functions like that. Like we sort of know this. Swear to God, if this involves 19 again. No, not quite. Yeah, not really. But it looks like really similar to this. Or we could even just redo 52 with that function. I don't know, it's not every function. It's not every, I swear we just saw this. Did we do it? Oh, there it is. There it is. There it is. F. Okay. Yeah. This is why I was like, oh, this is easy. So number 50 that we did last week, you can see is falling out of my brain now. This is the function that we are looking at on the right-hand side. We found them already. You can expand it into power series, and the question 50 was to find the coefficients. So you just get this recursive relation. Maybe I won't redo it. As you can see, I'm the kind of guy that likes to redo the problems when I forget them. But we'll call this AK. I don't remember off the top of my head what they were, but they're not hard to get. You just you just write down a power series that does this, you know? We had this recursive relation where basically this must equal 1 minus qz times this. Okay. I'm getting that from... He actually gave you the functional equation in the question on that one, on number 50. But it's not really hard to see. If you just plug in qz to this, you'll get a shift and you just correct for it. So it's pretty clear where this functional equation is coming from. And then on the right-hand side, you would get AK... oh, actually, sorry, I guess it's AKQK. And then you'd be subtracting q to the k plus 1, but also you're shifting up, so you get something like this. Oh, plus 1, sorry. Plus 1, there you go. So something like this times your zk's. So you get a statement like AK is AK q to the k minus AK minus 1 q to the k plus 1. So AK is well, that's frustrating. It's negative. I guess it just alternates. I don't remember that being part of it, but I guess it was. And then A naught, when you plug 0 into this, you'll get 1. So you do have that to start off with. So you can just iterate this. You're getting something like, let's see, if it was A1, I'd get the negative of that. So we have an alternating product of these guys. Unfortunately, these are not just odd, so I'm not going to bother to add them. I mean, we could add them up. It's q to the, but you get the idea. K plus 1? So let's see, at 0, or sorry, for 1, so for example, A1 would be the negative of q squared over 1 minus q. Fair enough. Damn it, why'd you do that? Let's make this a V. K goes from 1 to V. This is a V. And then this is q to the k plus 1, I suppose, right? So you could sum those up just to get q to the, or I suppose it's q times q to the, you know, you're getting something like q times q to the, but whatever. That's not so important because we still got this junk downstairs. Oh, wait, we could, nah, you don't want to mess with that. Anyway, we had this. So we have a formula for the decays. Looks like this. What did he say for 50? Yeah, 50, he did do that summing on the top. And he just left the bottom the way it looks. This is the... Now should there be a oh, he negated every one. You see that? I said -1 to the v, but he just flipped the order around on the denominator so that there was no negatives. But whatever, same thing. So for 58, yeah, he immediately refers to it as A. 50, there it is, applying 50 to get the A on the right-hand side. But other than that, it's the same. You just divide by, you know, this 1 minus q to the k. So that's a pretty straightforward one. Sadly, I must disappear. I wanted to finish 5960, but duty calls. I must go walk a dog. So we'll see about 59 and 60 another time. But thank you for popping in, ladies and gents. If I have room on this paper, maybe I'll do them later. But I have to disappear. Go take care of some things. So you have yourself a good day.